Next, what we're going to do is use the information that we know about asymptotes and about the first and second derivatives and intervals of increasing and decreasing, inflection points, concavity, and we're going to use all that and put it together to help us sketch a graph of a function, of a rational function. So we're looking at the function f of x equal to 1 over x plus 2, and we want to sketch a graph of this. Well, we've got about 7 different steps that we're going to go through to gain some information about this function before we graph it. And we're going to start with finding any intercepts. So with intercepts, we have both x-intercepts and a y-intercept. To find x-intercepts, we set our function value to 0. So we want to know, when is this function equal to 0? 1 over x plus 2. When is that equal to 0? Well, in order for the function to equal 0, because it's a fraction, it's a ratio, the numerator needs to equal 0. So when is the numerator 0? Well, the numerator is 1, so the numerator is never going to equal 0. So therefore, there are no x-intercepts. Next, we want to find the y-intercepts. The y-intercept, I should say. To find the y-intercept, we plug 0 in for x. We set x to be 0. So we're taking f of 0, plugging 0 in, we have 1 over 0 plus 2. So we get 1/2. So the y-intercept then is the point 0, 1/2. Next, we want to find any asymptotes. We have both vertical asymptotes and horizontal asymptotes. We'll begin with the vertical asymptotes. Now, to remember to find those, we first look at our function and we simplify it if it needs to be simplified by factoring the numerator and denominator and canceling out any common factors. Since our function is already simplified, our next step then is to set the denominator to 0. So if we set our denominator to 0, we have an x plus 2 equal to 0. Simplifying, we get x equal a negative 2. That is our vertical asymptote. Next, to find the horizontal asymptote, we look at the degree of the numerator and the degree of the denominator, and we compare those degrees. Here, the degree of the numerator is 0, and the degree of the denominator is 1. So in this case, the degree of the numerator is less than the degree of the denominator. So therefore, the x-axis, or the line y equals 0, is our horizontal asymptote. Next, we want to find our first and second derivative and their domains. I'm going to begin by rewriting the function f of x as an x plus 2 to the negative 1. So I'm going to bring the denominator up to the numerator, and that way we can avoid using the quotient rule. Instead, we can use the power rule here. So to find the first derivative, f prime of x, bring the negative 1 out in front, and then subtract 1 from the exponent, and then take the derivative of the inside function using the chain rule. The derivative of x plus 2, though, is just a 1. Alright, so our first derivative then is a negative 1 over x plus 2 quantity squared. Okay, so now let's find the second derivative. To find the second derivative, I'm going to view the first derivative with a negative exponent. So I'm going to think of it as a negative x plus 2 to the negative 2 power. So to take the second derivative, I'm going to bring the negative 2 out in front. So we're going to end up with a positive 2, x plus 2, subtract 1 from the exponent, so we get a negative 3, and then multiplying by the derivative of the inside, which is just 1. So our second derivative then looks like 2 over x plus 2 cubed. So there is our second derivative. Now the domain of the first and second derivative, we need to look at the denominator and realize that we create a 0 in the denominator when x is equal to a negative 2. So our domain then is going to be all real numbers except for negative 2. So our domain is all x such that x is not equal to a negative 2. And there's our domain of the first and second derivative. Next, we want to find the critical values of f. Recall that critical values occur when the first derivative is equal to 0, and also for x values for which the derivative does not exist. Let's begin by setting the first derivative equal to 0. So we want to set f prime of x equal to 0, and doing so we have a negative 1 over an x plus 2 squared, and we're setting that equal to 0. Well, since the numerator is a constant, the first derivative is never equal to 0, so there's no solution to this equation here. So there's no critical values created by the derivative being equal to 0. Now let's think about when the first derivative does not exist. Well, we said that the first derivative does not exist at x equal negative 2. Negative 2 was not in the domain. But x equal negative 2 is also not in the domain of the original function of f. So therefore we have no critical values. We have no critical values because there are no x values that make the first derivative equal to 0, and there are no x values for which the first derivative does not exist that are also in the domain of f. Next, we want to find any relative extrema and also the intervals of increasing and decreasing. To find relative extrema, and recall that relative extrema are relative maximums and relative minimums, what we do is we use critical values to find those. But since there are not any critical values, then that means that there are no relative extrema. Now, to find intervals of increasing and decreasing, typically we take the x-axis and we divide the x-axis up around the critical values and then use the first derivative to determine whether the first derivative is positive or negative, to determine whether it is increasing or decreasing on those intervals. Since we don't have any critical values, what we're going to do instead is use x equal negative 2, which is where our function is not defined. So we divided our number line up around negative 2. So we've got the interval negative infinity to negative 2, and then the interval negative 2 to infinity. So we can pick a test value out of each interval. For example, I could choose a negative 3 out of this first interval. Now, if we plug negative 3 into our first derivative, f prime of negative 3, what we should get is a negative value. This is less than 0. So this tells us, since the first derivative is negative, that the function is decreasing on this interval. So we are decreasing on the interval negative infinity to negative 2. Now let's choose a test point out of the second interval from negative 2 to infinity. For example, I could choose 0 as a test value. If we plug 0 into the first derivative, f prime of 0, we also get a negative value. So this tells us that f is decreasing on this interval as well. So we are decreasing on the interval negative 2 to infinity. Next, we want to find candidates for inflection points. Recall that we find possible inflection points by setting our second derivative equal to 0. So setting our second derivative equal to 0, we're setting 2 over x plus 2 quantity cubed equal to 0. Now, since the numerator is a constant, this is never equal to 0, so there's no solution to this. So there's no x values for which the second derivative is equal to 0. We also can consider where the second derivative does not exist. Now, we said that the second derivative does not exist at x equal negative 2. Negative 2 is not in the domain, but also negative 2 is not in the domain of f. So therefore, we have no inflection points. Next, what we want to do is determine the concavity of the function. Typically, to determine concavity, whether the function is concave up or concave down, we normally use the inflection points. But we found in part f that there were not any inflection points. So what we will use is we will use x equal negative 2, since negative 2 is where the function is not defined. So we divide our number line up into two intervals around negative 2. So we have a negative infinity to negative 2, and then the interval negative 2 to infinity. And we'll pick test values out of each of these intervals and determine the sign of the second derivative. Recall that when the second derivative is negative, we are concave down, and when the second derivative is positive, we are concave up. So in the interval negative infinity to negative 2, I could choose a negative 3 as a test value. if we plug negative 3 into the second derivative, so f double prime of negative 3, what we get is a negative value. It is less than 0. So since the second derivative is negative, then this tells us that the function is concave down on this interval. Next, if we choose a test value out of the interval negative 2 to infinity, for example, we could choose a 0. Plugging 0 into the second derivative, we get a positive value. We get that the second derivative is positive. Since the second derivative is positive, this tells us that we are concave up on the interval negative 2 to infinity. So now we're going to use all the information that we've gathered from steps A through steps G to now sketch the graph of this function. So you may have to flip back through to see the results that we gathered in all of these steps. I'm going to begin by graphing our x and y intercepts. Now recall there weren't any x-intercepts, but we did have a y-intercept at 0, 1/2. Next I'm going to graph our asymptotes. We had a vertical asymptote at the line x equal negative 2, and recall we used that to help us determine what was going on to our function away from that asymptote, whether we were concave up, concave down, or whether we were increasing or decreasing. So I'm going to graph the vertical asymptote. And then we had a horizontal asymptote at the line y equals 0. So now I've got the intercepts graphed and I've got the asymptotes graphed. Let's begin by drawing the right side of the graph. So everything to the right of the vertical asymptote. We said everything to the right of the vertical asymptote we are decreasing and also concave up. So to help us out with graphing this, we can choose a couple x values to plug into the function. If we plug a negative 1 into our original function, we get 1 as a function value. If we plug a positive 2 into our function, we get 1/4 as a function value. So let's plot those points on our graph and then connect these points to graph the right side of this graph, keeping in mind that our function is decreasing and concave up. So there's part of our graph. Notice that we have no x-intercepts, so we will not cross the x-axis, but as we go off to positive infinity along the x-axis, our function does approach the x-axis. And then as we approach x equal negative 2 from the right, our function is approaching positive infinity. Next, to graph the left side of the graph, we can choose a couple x values. For example, we could choose a negative 3 and let's say a negative 5, for example. Plugging negative 3 into our original function, we get a negative 1. And then plugging a negative 5 into our original function, we get a negative 1/3. So there's a couple additional points that we can plot on the graph. We also know that when we are to the left of the vertical asymptote, that our function is decreasing and we are concave down. So connecting those points, there's the rest of our graph. Notice as we approach the vertical asymptote from the left, as we get closer and closer to a negative 2, our function is approaching negative infinity. Also notice how as we head off to negative infinity along the x-axis, our function is getting closer and closer to that horizontal asymptote at y equals 0.